The last 6 examples are going to look at how we can apply these 5 theorems. Look at every problem kind of like a multiple choice problem, because you can use a process of elimination. If I think about each of these, so if I think about number 1, and I've got side, 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 angle, side, angle, side, angle, 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 side, and HL as my choices. First thing I'm going to notice is I don't have a right triangle, so it can't be HL. I don't know the third side, so it can't be side, side, side. So now I'm left with just a couple of choices. Do I know the side in between the 2 angles? I don't know this side down here, so that one is not a choice. The difference between side, angle, side and angle, angle, side. 2 angles with a side outside for angle, angle, side, or 2 sides with the angle between. So these 2 sides, do I know the angle in between? Nope. What I do know are 2 angles and the non-included side. Or you could go the other way, 2 angles and the non-included side. And they match up. Picture's getting messy. They correspond, angle, angle, angles, with these 2 triangles. And so we are looking at angle, angle, side for this triangle. Now, if we look at the next one, we have a right triangle. So we could potentially have HL. So let's check that out first. We know the hypotenuse is congruent to the hypotenuse, and we know one leg. And that is exactly the criteria for HL. Now, the next one brings up an interesting situation that you should look for regularly. There's only a few things we can assume from a picture, and that's really a dangerous thing in geometry. We always want a reason for what we know. But a couple of things that you get from a picture are that 2 angles form a linear pair. You can take that. If the picture looks like a straight line, it is. It's a linear pair. And vertical angles. And so when I see this picture, I usually refer to it as a butterfly picture. Right here and right here are vertical angles. And we know vertical angles are equal. And so if I mark those vertical angles, I now can see that I have an angle, the side between them, and another angle. And so these 2 triangles are congruent by angle, side, angle. So don't forget to look for those vertical angles and mark them because they are used as part of your triangle congruency. We're going to come back to 4. When I look at 5, I know 2 sides and an angle. Well, 2 sides and an angle, that's my only choice, side, angle, side. And remember, I have to know the angle in between the sides. And so I don't, so I cannot prove these are not congruent. I can't prove it. And if I look at number 6, again, I've got a right angle, so I'm going to look first to see if I have HL. Indeed, I know the hypotenuse of each one, and I know one leg of each one, so these 2 would be congruent by HL. So I'm going to jump over to this picture to talk about number 4. Same picture. It appears initially that we only know one side and one angle, which is not enough. But we have a new idea that we have to talk about when it comes to congruent triangles. And I'm going to draw this picture because it makes it a little easier to see. So if I look at triangle ABCD here, got 2 triangles. And if I highlight this ABD, and I highlight this triangle, what happens right here in the middle? My line turns green because they share that side right there. And because they share it, if I went to draw them out separately, if they weren't connected, and I had A, B, D, and B, D, C, something has to be equal to itself. This sign right here, they share it. It's overlapping. It's doing double duty on each side. That counts, and that is called reflexive. the reflexive property. If an angle or a side is shared, it equals itself. And so in this case, that side right there is shared. And if I highlight them again, one in yellow and the other in blue, you'll see the magic of the green overlap. That shared side is equal to itself because it's used twice. Now, when we go to start naming them, notice that this one is a twist. If I threw some coordinates on here, A, B, C, and D, my first triangle, triangle A, B, D, would be congruent to triangle angle A matches up with C. Now notice this angle right here and this angle right here are twisted. So this ABD actually matches with CBD if you think about cutting them apart and flipping them, and vice versa on the switch. So these two are in different orders because there's a twist if I have to put these together. Down here, this is a fold. If I fold this in half, they'll match up. So down here, triangle A, B, D would be congruent to triangle A corresponds to C, C, B, D. And you see BD matches up with BD because this just folds right in half. The reason this top one is congruent is by side, angle, side. Now that reflexive side is something that you can take from a picture, so you always have to look for it. It can also happen with angles. A reflexive angle would look something like this. Whoops, I drew that picture wrong. And I'll do them in different colors. And so you can see they share that angle if you were to separate them out.